In this video, we will talk about what linear approximation is. And I want to motivate this with an example, which says, suppose we want to estimate the cube root of 28 without a calculator. So what I'm going to do is, because I'm trying to find this cube root of 28, I'm going to let my function f of x be the cube root of x, and then think about what this function's graph looks like. Okay, so I'm going to draw some axes. And the graph of the cube root of x looks like it sort of snakes upwards like this, and then it continues onwards and kind of starts to snake that way. So it's a bit like the square root of x graph function, except we're allowed to plug in negative values for x into this because we're taking a cube root. All right, so that's why there's this portion of the graph over here where x is negative. All right, so we are interested in kind of figuring out, well, when I plug 28 into this function, what is that y value? What is that output? So, of course, I can call this cube root of 28, but I'm interested in estimating that value. Okay. So let's talk about the idea that we're going to use. So our idea is going to be to first find a number, I'm going to call it a, that's close to the number, the input that we care about, the 28. So close to 28, for which we know the output. We know how to find f of a without a calculator. So for this function, what number can I plug in that's close to 28, such that when I cube root it, I know what that is? Well, that's just 27. So we know that if we let a be 27, I know how to cube root 27. So since the cube root of 27 is just 3, okay, so I'm going to draw that on the graph. So I'm not going to draw it to scale. I want to put it a little further away just so I can spread out my picture. Let's say 27 was here. And at 27, when I plug that into this cube root function, the y value is going to be 3. Okay, so my next idea is going to be, now at 27, my x is 27, I'm going to draw a tangent line to the curve. So my tangent line is going to look something like this. And with the tangent line, if I could plug 28 in the equation of the tangent line, that would give me this point. And that point is pretty darn close to the actual point that we care about. So this is going to be my approximation. And that is pretty close to the actual point. So this is the heart of linear approximation. It's all about finding a tangent line at a point close to the point that we care about, and then using that equation of the tangent line and being able to plug something into that tangent line. Okay, let me just write down in words what we just said. So the next step is, well, we draw a tangent line. Draw a tangent line at that point, at a comma f of a. And then we are going to get its equation. So to get the equation of this line, we will need to know the slope and a point. So we need the point and a slope. All right, so for the point, I know my x coordinate is 27, and the y coordinate, well, we know that already also. It was the cube root of 27, which is 3. Okay, we are ready for the slope, and the derivative is going to tell me the slope. So for the derivative, remember, a cube root of x is just x to the 1/3. So if I do power rule on that, we'll get 1/3 x to the negative 2/3. And now let's plug in 27 in for x, because that's the point at which we were drawing the tangent line. So I get 1/3. If I bring this x to the negative 2/3 to the denominator, the exponent will become positive 2/3. And we're plugging in the 27 for the x. All right, so now let's evaluate this. We get 1/3. So this means I need to cube root the 27 and then square that. And that is 1/3 times, let's see, cube root of 27 is 3. So we get 3 squared. So overall, this is going to be 1 over 3 times 9, which is 27. So 1 over 27, that is my slope. All right, so we are ready to write down the equation. So the equation is y minus the y coordinate, which is 3, equals the slope, 1 over 27, times x minus the x coordinate of the point, which is 27. All right, and as we were showing in the picture, well, once I have the equation of this tangent line, now let's plug in x equals 28 into it so we get our approximation. All right, so let me write that down in words. So now we're going to plug in the actual x value into our tangent line equation. All right, so doing that, so our equation is y minus 3 equals 1 over 27, and we're going to plug in the 28 in for the x. So 28 minus 27. And if I simplify this, let's see, let's just isolate y. I'm going to add 3 to the other side, and we'll get 3 plus. This is 1 over 27 times 1, which is 1 over 27. And if we get a common denominator, I have to multiply the 3 by 27 over 27, which will give me 81 over 27 plus 1 over 27, and that is 82 over 27, and that is my estimate. If I were to put that in decimal form, this is 3.037, and then it just repeats those 3 digits. All right, so that is our estimate right there. And if we look at our picture, our approximation was higher up than the actual point. So our approximation is going to overestimate the actual value. So this overestimates the actual value. So it turns out that the cube root of 28, if we write the actual decimal form of this is going to be approximately, I'm going to write several decimal places. It's approximately 3.036589. Those are the first 6 decimal digits after the decimal point. So I'll put a dot, 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 because it does go on forever and it doesn't repeat. This is going to be some irrational number. And if I compare that to our approximation was 3.037, and the 037 is repeated, and that is super close. So we were pretty close here. Okay, so I want to make a note of something. So the note is that the closer A is to our actual x value, I'll just call it x, to the actual x value, the better our approximation is in general. That won't always be the case. Sometimes I could have some weird graph shapes where even if the a value is close to x, we don't always get a super, super close approximation, but in general, this is going to be the case. All right, so next I want to introduce some terminology. So if we isolate the y in the tangent line equation, we call this the linearization of our function f at a. Okay, and I'm going to call this linearization. It'll be a function. I'm going to call it L of x. Okay, so let's write down what L of x is for our example. So I'm going to go to my tangent line equation. So that was here, and I just want to isolate the y. So all I got to do is just add the 3 over to the right, and that'll be my linearization function. Okay, so if we do that, we'll get L of x equals 3, we're adding the 3 over, and then plus what we had there still was 1 over 27 times x minus our value of a, that was 27. So that was the linearization for this specific function. Let me also write the general formula. So the general formula, okay, is L of x equals, so the 3 was our y value at a, so that is f of a. 1 over 27 was the slope of the tangent line, that is f prime of a, and that's getting multiplied by x minus our a value. That's the general formula for linearization. I personally wouldn't memorize this. I just remember, oh, it's just the equation of the tangent line once I get the y by itself. And convention is I call that thing L of x for linearization. So in terms of our goals for this section, I'm going to check off goal 2. We now know what the linearization of a function is at a. I could check off this first goal as well. We now know how to use linear approximation to estimate functions at non-nice values. But I'll wait until our next video where we do one more example.